Hello there. Welcome to our continuing adventures of Chapter 1 in Biochem. In today's webcast, we're going to focus our attention on acid-base chemistry. As we do today's webcast, I'm going to be making one change based on a suggestion from viewers like you, and that is I'm going to have the computer do a little bit more filling in the blank so we can spare you a little bit from my handwriting. Let me know how that change goes. If you want me to go back to doing more fill in the blanks with writing things out, just keep me posted. So, acid-base chemistry, why do we care? Bottom line, it turns out that the protonation state and properties of biomolecules are uber critically dependent on ionization state. So whether something's protonated or deprotonated will have huge impacts on the behavior of biological molecules and chemical species in general, but especially biological molecules. We're going to be talking about gazillions of examples throughout the course. Just going to briefly mention three here that we'll deal with a little bit now and a lot later. The first one to mention is this idea of membrane permeability. So you remember that in our first or second lecture of the course we talked about the cell membrane, and we said basically the job of the cell membrane is to be a barrier or a container to keep things on the inside separated from things on the outside. But you remember that a lot of the insides and outsides are aqueous in nature, so you need to have a strategy to prevent free movement of molecules that you don't want just to start wandering out of cells. One way that this happens is through altering the ionization state. So here's just an example of an organic molecule now. It's a phenol that can exist in either a protonated or a deprotonated state, because you remember that phenols, unlike typical alcohols, have pKa's that are much lower. But depending on the ionization state, this will be either very, very soluble in aqueous systems if it's protonated, or it will be very, very insoluble if it's protonated. And I have a cool demo that I'm going to show you about this on Friday. But again, as a key reminder of something you learned about probably in both Gen Chem and Organic Chem, you can have very nonpolar molecules that become very soluble in water simply by making an ion out of it. And when you make ions or charged species, a lot of times their solubility increases tremendously in aqueous systems. Another prime example of the protonation state being key to biological activity is that we know that when we think about enzymes, they show tremendous pH dependence. If you vary the pH of a solution that you're studying for a particular enzyme by even a half a pH unit, you can drastically alter its activity and its structure. And in living systems, as many of you know, if you change the pH of a living system away from home base, which is around 7.2 to 7.4, you can kill that person by changing the pH by more than a half to a full pH unit. And the reason for that is when you change ionization states, it will change activities of key enzymes, it will change the folding properties of biological molecules, and basically everything goes to heck in a handbasket. The next one is an example we'll do a little bit today, and then we'll talk a lot more later in the course, and that is using hemoglobin as a specific example to show this concept. So, oxygen affinity of hemoglobin. You guys all know that when we think about hemoglobin, hemoglobin is the molecule in red blood cells that's responsible for transporting and delivering oxygen to respiring tissues. So just in the way of quick background, remember that when you're exercising, which some of us do and I probably should, during strenuous exercise anyways, our tissues are metabolizing quickly to give us the energy we need to keep ourselves moving forward. So when we're exercising strenuously, we're going to be using up the oxygen concentration quickly, and that's going to cause the concentration of CO2 to rise in our bloodstream. Again, through metabolism, you consume O2, and ultimately you produce CO2, which we exhale as we breathe out. But when we breathe out CO2, it has to get to our lungs, and ultimately when CO2 is produced in our tissues, that's going to cause the concentration of acid to build up. And the way it's going to do that is partially through enzymatic processes, but the bottom line from Gen Chem, you may recall that when you dissolve CO2 in water, CO2 will actually do a reaction, an equilibrium process with water, where CO2 will produce bicarbonate, which is not what we care about at the moment, but it will also produce H3O+. So it will increase the acid concentration in our blood simply by its presence. And like I said, there's enzymes that are actually involved to help regulate the direction of this process, but that's another story for another day. So anyways, when we think about the impact of this, we said just a minute ago that hemoglobin is responsible for carrying O2 to our bloodstream. So if we're breathing in fast during exercise, we want to be able to get oxygen to our tissues as fast as humanly possible. So it turns out that the way our system is set up, the way our hemoglobin molecules are set up, is that if the acid level in our blood tissue rises, that's a chemical trigger for having hemoglobin do a better job at releasing oxygen to the tissues when it gets to the spot where it has to drop off the O2. Now, how does it do that? Ultimately, it's through an acid-base reaction. So it turns out that there is an amino acid side chain in, or actually I believe it's the amino group of the protein. We'll revisit this later. But we have an amine group on hemoglobin that will react with the acid through an acid-base reaction. So we have our base and we have our acid, and that, if the acid concentration is increased, so if this value goes up, that's going to shift the equilibrium to the right through Le Chatelier's principle, protonated that group, and when this group of hemoglobin gets protonated, that changes some of the salt bridge type contacts in hemoglobin, which ultimately leads to complex structural changes, which ultimately helps to shift the equilibrium for the release of oxygen from the iron in hemoglobin. So it's totally taking advantage of ionization state. And again, we're going to be talking about that process in a lot more detail in the coming chapters. But just one, I think, nice example of the whole issue of protonation state affecting biological activity. All right, so that's kind of the overview. What we're going to do now is we're going to move on to some fundamental general chemistry, kind of, again, to blow off the dust. And so first, to do that, we're going to think about all the way back in the beginning when we started talking about acid-base chemistry, and we're going to talk about the ionization of water and pH. So, thinking about acid-base properties in water, remember that once upon a time, way in the beginning, we said that to a small extent, water molecules, which prefer to be H2O most of the time, occasionally and very infrequently undergo self-ionization. So remember, or know that we can talk about an equilibrium process for water, which is usually called the Kw equation, which says that the Kw constant is equal to the product of the H3O plus and OH minus concentration, which numerically is equal to 1 times 10 to the minus 14. So when we say 1 times 10 to the minus 14, the magnitude of that equilibrium constant is extremely small, but non-zero, which means that water has the ability to occasionally bump into itself, transferring an H plus from water molecule 1 to water molecule 2 to result in the production of a hydroxide minus and an H3O plus. But again, in pure water, it's a very small extent, and if we measure the electrical conductivity of water, as some of you know, when you're getting easy pure water from the analytical chemistry laboratory, it has very high resistance, 18 megaohm centimeters, which is a fancy way of saying pure water doesn't conduct electricity to any meaningful extent because these values are really low. But we know that when we add acids or bases to waters, that can greatly shift the relative concentrations of H3O plus and OH minus, and ultimately, when we adjust those values, we're going to get concentrations that are a lot different from 1 times 10 to the minus 7 for each of these two guys, which is going to have major impact in terms of the chemical processes that take place in acids and bases. So the next little memory item is to say that although we're at the chemical level usually dealing with numerical values on the order of 1 times 10 to the minus 3rd molar, 0.1 molar, 0.5 molar, 1 times 10 to the minus 6 molar. It's kind of messy to use those numbers in the real world, so then we have this thing called the pH scale, which is a nice way of expressing ugly concentrations in a nice, pleasant way in the real world. So you know about the pH scale. We're not going to go crazy with that, but you know that to get a pH from a concentration, you take the negative log of whatever the thing in question is. It's also worth knowing that from Gen Chem that there's a cool little trick which says that if you know the pH, you actually also know the pOH, and that the sum of these two guys always add up to 14. So if you calculate the concentration of hydroxide, or you determine its pOH to be 3, that tells you that its pH is 11 and that it's a basic solution. So just blowing off the dust from things you've seen once upon a time. Now, one thing I want to add to this slide right here is to actually say a little bit more about the KW and where it comes from, which is something Dr. Inger probably didn't do once upon a time. So I want to think about this just very briefly from a more quantitative equilibrium treatment. So you know that when we have the KW equation, that we tend to simplify it and just say it's the H plus concentration times the OH minus concentration. But technically speaking, we can write an equilibrium process for this. And you know that when we tend to write the equilibrium expression, so this is the equilibrium expression for this equilibrium process, we know that the drill is usually to say KEQ equals products raised to the appropriate powers. Since there's a coefficient of 1 in front of both of these are both of the first power, over the reactant, as it were, concentration. Now in Gen Chem, you tended to say whenever you had something like water, or pure systems where their concentrations don't change, we tended to ignore the contributions from these species. But you can actually do this. You can actually include that in the situation. Again, we normally just throw it into the equilibrium constant, but it is possible to know that the equilibrium constant for this full process, including all of these concentrations, is actually 1.8 times 10 to the minus 16 molar at 25C. But if we want to determine the concentration of this particular value, we can do that from water's density. So if we determine the concentration of water using a density of 1 gram per mil at 25, it turns out that water comes out to 55 molar. So where this KW actually comes from is that the KW absorbs, so through a rearrangement of this algebraic expression, it absorbs the concentration of water and the equilibrium constant. And when you then factor these things into one term, that's where this 1 times 10 to the minus 14 comes from. So we're not cheating when we give you a KW. We're just saying that the magnitude of the water concentration doesn't actually change during the process to any appreciable extent. And so we can simplify our equilibrium expression to only worry about the H plus and the OH minus, getting the 1 times 10 to the minus 14. So we haven't like fundamentally changed what we do with equilibria, where we ignore the reactant. We just tend to absorb it into the equilibrium expression. All right, so that's all nice and good, but we should talk now about how acids and bases behave in aqueous solutions. And so again, we're going to start simple, and then we're going to work towards examples that will be useful for our purposes. So in aqueous solutions, remember that we can have strong acids and bases, or we can have weak acids and weak bases. So the question for you guys is, what is the key difference between a strong acid and a weak base? Over time, you may just say, well, strong acids are things like HCl, NO3, sulfuric acid, and whatnot. Weak acids are things like acetic acid and what have you. But along the way, you may have forgotten what the fundamental reason is why. And ultimately, the reason why is that it comes down to the percent ionization of the acid in aqueous solutions. So as a reminder, strong acids will react with water in a quantitative fashion. So as an easy example, we'll just use HCl. What you know from Gen Chem is that HCl is a strong acid, but again, the reason it's a strong acid is that if you take HCl gas and you dissolve it, or more appropriately, react it with water, that reaction 100% of the time, or close enough for government work, will go from left to right quantitatively producing H3O plus, aqueous, and Cl minus aqueous. So it's perfect in essence. It goes completely from reactants to products. In contrast, weak acids, or weak bases, are governed by equilibria processes, which means that there isn't just an arrow effectively going one direction. There really is an arrow of a fairly decent magnitude going in the reverse direction because it's governed by equilibrium conditions. So what we're going to do now is to think a lot about equilibrium conditions and to talk about factors that affect why an acid is strong or weak. So let's just consider acetic acid, our favorite friend. So here's the equilibrium process for what happens when you put acetic acid in water. The acidic H from the acetic acid molecule will react with water occasionally to produce H3O plus and acetate, but it's an equilibrium process. It's not uber favored to go from left to right. And in fact, if you have a high concentration of H3O plus and acetate, some of these molecules will slam back into each other going in the reverse direction. Again, that's very different from a strong acid. But we can write the equilibrium expression for this process. So we can say that KEQ equals products over reactants. So we have our acid, acetate products on the in the numerator of the expression, and then we have the acetic acid molecule in the denominator. Again, we tend to leave out water because it gets absorbed into our equilibrium constant. Now, because this is an equilibrium process for an acid, we change KEQ and we call it Ka because it's the equilibrium expression for an acid. And one thing that's often convenient for us to do is that once we write our equilibria expression, it's often convenient to take the value of Ka and to take the negative log of that value as well. Again, Ka values tend to be crazy, ugly numbers too. So just like with pH, where we take the negative log of H3O plus, we can also take the negative log of our Ka value, and we can get what's called a pKa. In case you haven't thought about pKa in a while, remember that pKa reflects the ease with which an acid will give up its proton. That is, the higher the pKa, the more tightly the proton is held. And it turns out, and I'm going to show you this through example, this depends almost completely on the stability of the charged species. So what I'm saying with this statement here is that molecules that have low pKa's are very acidic. So low pKa's are very acidic. High pKa's in water will be less acidic. And so let's kind of work through a quick example to illustrate the point. So we're going to use acetic acid as our parent example. So we just got done showing you that we have an acetic acid to acetate equilibrium process. And if you calculate the pKa, or look up the pKa value of acetate, or acetic acid, sorry, in a book, what you'll find is that it comes out numerically to around 4.76, and that may be even a number you memorized. However, if we have derivatives of acetic acid, and so in our second example, we substitute an H for a Cl, what's that going to do to the pKa of the system? That is to say, if we want to think about how this equilibrium process is influenced by the presence of Cl, what's it going to do? So looking at, or returning to the previous slide where we say that the pKa tends to depend almost completely on the stability of this charged species, if we have acetate, in all of these different situations, we're going to have a negative charge of our product. Well, what factors are going to either stabilize or destabilize our product? And this feels very Dr. Jancy-esque. So if we have a negative charge, we know that for acetate, we can write two resonance forms that delocalize the negative charge over these two oxygens, and that partially accounts for why acetic acid is a fairly reasonable acid to some extent. But if we then also make a change where we pop an H off and replace it with a Cl, what's that going to do? What do you know about Cl? Well, what you know is that Cl is going to help to pull some electron density away from carbon because chlorine has greater electronegativity, and that means you can now further spread out the charge across the molecule by having this inductively withdrawing chloro group. And when you do that, that's going to allow more delocalization of the charge across the entire molecule, which is going to cause the pKa to become lower, down to 2.87, which again means that it's more acidic than is the parent compound. And we can continue this process along. If we go to dichloroacetic acid, okay, now we have two inductively withdrawing chloro groups, and that's going to drop the pKa by another full pH or pK unit, which again, pK and pH have a correspondence. Moving a pK from 2 to 1 is also a tenfold change in the equilibrium constant. So this is even more acidic. And finally, if we go to trichloroacetic acid, you guys may have heard of trifluoroacetic acid in organic chem. If you go to that, now we have a pKa that's all the way down to 0.36, and in this series, that's going to be the most acidic because now you have the ability to delocalize that charge or spread that charge out across the molecule more effectively. So you're stabilizing the charged species. When you stabilize the charged species, it makes it more likely to go from left to right, and you become more acidic. And so that's kind of a reminder of pK. Now again, when we think about amino acids in proteins, there's tons and tons of examples where amino acid side chains undergo this exact chemistry. Now, as one final point, one thing that we're not going to talk in detail about now, but I want you to sort of plant as a seed, so maybe even put a little asterisk by this when you see problems like this showing up when we move into amino acids and peptides, is that it turns out that if we have an enzyme system, the inside of the protein can greatly impact the effective pK values of amino acid side chains. And ultimately, I want you to think about why that might be. And I'm just going to kind of preview it now and give you a hint. If we have an amino acid side chain, okay, inside of an enzyme active site, so we're going to say this is a very hydrophobic medium, hydrophobic environment, which means there's not a lot of charge going around. If you have an amino acid side chain, like a carboxylic acid group, is it going to be more or less likely to be, quote-unquote, want to be in the protonated form in a hydrophobic environment or deprotonated in a hydrophobic environment? And I'm not going to answer that question now, but this is something I want you to think about. I think if you think about it for just a minute, you'll be able to come up with it. But this is an issue that you'll see as we move forward in the course. So just planting a seed. All right. So that's kind of like the theory in the background of pKa's and whatnot, but now we're going to turn to what I think is the most important aspect of this webcast, which is recognizing how these equilibrium processes affect a property in acid-base chemistry known as buffering. So we're going to talk now about buffering. And it's going to go something like this. We have to kind of set the stage. So back in Gen Chem, you learned that strong bases react quantitatively with weak acids. That is to say, it's not an equilibrium process. A strong base will react with an acid and say, you are giving me your H plus because I'm a strong base and I want your H plus. Take it, weak acid, that's how it is. Likewise, you also learn that strong acids can react quantitatively with weak bases. But if you do a titration of the reaction of a strong base with a weak acid, you get a very interesting phenomenon. And for those of you that took Gen Chem lab at Valpo, you all did an experiment where you measured the pH of a system that had a weak acid in it as a function of added hydroxide. And what you saw is that in a certain zone of the experiment, the reaction or the change in the magnitude of the pH appeared to, I'm going to say slow down, but we don't really mean kinetics here. It didn't change as quickly with added hydroxide. And we call this buffering, resistance to changes in pH when strong acids or strong bases are added to a system over a certain range. But the cool thing about buffering is that it gives you a great way of experimentally determining the pKa value. The pKa value is the point at which you are half titrated, the point at which you've added a half equivalent of hydroxide to your weak acid. So at this point, 50% of your molecules are in their acid form, 50% of their molecules in their conjugate base form. But what you notice at this point where there's the least amount of change in the buffering region is that the pH values around this pKa value don't change as quickly, again in quotes, as a function of added hydroxide. So what we know about weak acids and weak buffers is weak bases is that they tend to resist changes in pH near their pKa. And so what we're going to do now is to talk about that and work through lots of examples to show you both conceptually and quantitatively how this process works. And just as a quick comment, when we think about buffering, buffering is maximal plus or minus 1 pH unit away from the pKa. So if you have a molecule that has a pKa of 4.76, it tends to buffer fairly well from 376 to 576, and now we're going to show you why. So to think about buffering in weak acid, weak base systems, we're going to turn now to an awesome equation that you will love, love, love in biochemistry, known as the Henderson-Hasselbalch equation. And importantly, the reason we're doing this is that because buffering is extremely important to biological systems, that is, you want to prevent rapid changes, or not rapid, darn equilibrium. We want to resist changes from a thermodynamic point of view in biological systems. It would be ideal to have a mathematical expression that allows us to relate pH to pKa and weak acid base concentration. So we're going to do that now, and we're going to re-examine the weak acid equilibrium expression. So if we have any equilibrium process for a weak acid, you will have the following equilibrium expression. You have the conjugate base times the acid over the acid in its protonated form. And again, this is, you could use acetic acid as your example here. But we'd like, again, to be able to relate pH to pKa. So what we're going to do at this point is we're going to take the negative log of both sides of the equation. In algebra, when you do something to one side, you do it to both sides. So if we do that, we're going to take the negative log of Ka, and we're going to take the negative log of the entire term A minus times H3O plus all over HA. And when we do that, using a couple of handy-dandy properties of logarithms, we can then say that the negative log of anything is the p of that thing. And so on the left side, we'll end up with pKa. On the right side, again, because of properties of logarithms, we can separate these parts, and we can say that we have pK equals pH minus the log of A minus over HA. And again, if you need to review that, there's cool wikis that show you properties of logarithms. But anyways, if we want to have a nice expression that allows us to quickly solve for the pH of a process under any set of conditions, we can then have, we can rearrange this equation, and we come up with the final form of the Henderson-Hasselbalch or HH equation, which is pH equals pKa plus log A minus over HA. And this is an awesome, awesome, awesome equation that will be extremely useful to you as we move forward in biochem. Now, not to be too flippant here, but if you actually take a closer look at this equation, what does it kind of remind you of? Well, if you said, gosh, this looks a lot like the delta G equation we had about a webcast ago, you'd be exactly right. We have our actual pH, which would be kind of like our actual delta G, equals delta G naught, so the delta G under a standard set of conditions, that's going to be kind of like our pKa, because the pKa is a defined point at which you have a 50-50 mixture of your acid and its conjugate, an equal mixture, plus a correction term. Now in this case, our correction term is, for delta G, is RT ln Q, but remember that ln Q is just products over reactants. Products over reactants. So really, if you know this equation, you kind of know this equation too, because their form is very, very similar. But now that we've derived a form, we can do fun things with it. Before I go on to the next slide, I want to quickly make one little comment, and this will show up in an example problem, is that when we have this form of the equation, we write it and we're making an assumption that the product and reactant concentrations are truly under equilibrium conditions, and sometimes that can cause us problems. But we'll get to that when we get to some examples here moving forward. So, thinking about the importance of the Henderson-Hasselbalch equation, we're going to return now to our plot that we showed you a minute ago. So again, this is our titration of a weak acid with a strong base. But now we're going to think about it in light of the HH equation. So pH equals pK plus log base over acid, products over reactants. And we're going to say that if you check it out from a mathematical point of view, we told you a minute ago that buffers are good plus or minus 1. Well, let's think about that. If the acid and base concentration are within a factor of 10 of each other, the pH change is going to be small. So if we take log 10 means that we're going to be product favored, okay, more in the base form than in the acid form. Log 10 is equal to 1, so the pKa plus 1 is going to give you a pH that's 1 pH unit higher. So if the concentrations are within a factor of 10 of each other, you're only getting a 1 pH unit change of your away from your pKa. If we then say if we have the condition where the base concentration is equal to the acid concentration, that means this over this is the same. Log of 1 is, well, you know what that is. That's 0, which means that'll be the point at which we're at the pKa. So just kind of trying to show you how you can just think about the mathematical representation of what's going on to relate it back to what we see in a titration curve. But the key thing is that this equation is going to be great because we're going to be doing a lot of experiments or calculations or understanding processes where we need to know the ionization state, and this becomes a great shortcut for quickly determining what the concentration of the base part of a molecule is, the base fraction, and the acid fraction of a molecule is, which will help us to understand the behavior of the system under question.